Hi all, my name is Joseph Nemi, and I'm going to be presenting on my project 2D channel flow over geometries using Lattice Boltzmann method. For my project goals, I am looking to simulate flow across both the square and circle geometry inside of a 2D channel flow. It is a common test case for turbulent flow, which I have modified to look at lower Reynolds numbers. By the end of the tests, I should be able to reproduce the streamlines seen here for the square impediment. I also hope to simulate different angles of attack for velocity and understand how changing that angle of attack affects the simulation. For my solver, I chose Lattice Boltzmann method. As a brief overview, it is a method where microscopic particles are tracked along lattices using distribution functions. For my simulations, I used the D2Q9 lattice with a BGK collision operator. My most widely used boundary condition was bounce back. The condition came in two forms: stationary wall and moving velocity. The stationary wall was used at the top and the bottom of the channel, as well as on each face of the square geometry. The modified bounce back proposed by Zhu and He was used for my inlet flow, allowing for momentum to be added and conserved for each distribution function. For my outlet, I used extrapolation to approximate the distribution at the boundary. This was done using a second-order polynomial. While this method can be somewhat unstable, for the simple flow being tested, it did not cause any significant errors. For my boundary conditions at the circle geometry, I used a method for curved surfaces outlined by Yu et al. It is difficult to account for curved surfaces using traditional bounce-back approaches. While it is possible to set the velocity inside the circle to be 0 and continue calculations, this provides inadequate accuracy around the geometry. Therefore, the bounce back is calculated to account for the momentum transfer at the surface itself. This is done through interpolation. First, the solid nodes on the inside and the fluid nodes on the outside are interpolated to one point on the surface, denoted by xw. The distribution function at the surface is then adjusted using interpolated velocities. Finally, the distribution function is interpolated back to the fluid node and calculations are continued. For my initial conditions for the problem, the microscopic velocity was set to 0.1 in the x direction for 0 angle of attack. To adjust for the angle of attack, the inlet velocities were modified according to sine and cosine functions, maintaining the magnitude of the initial microscopic velocity. By using this method of modification for my input velocity, it allowed for me to achieve a simulated angle of attack without rotating the geometries. Here are the results for my square geometry tests, which were all carried out at 100 Reynolds number. On the left I have my streamlines, and on the right I have my x velocities. The problem was validated for convergence through two methods, L2 error norm and spatial. L2 error norm was calculated on each iteration for x and y direction velocities. The solution was deemed converged, and at steady state, once the error was reduced to 10 to the negative 7th. Spatial convergence was tested using multiple grid sizes from 26 by 26 to 201 by 201. Generally, 101 nodes was acceptable for these studies, and spatial convergence rate was around 1.3. In order for the simulation to match literature results, velocities need to be streaming along the square geometry, which we can see in the streamline plot. We also want to see curving and vorticity at the tail of the square geometry, which we are able to achieve, and this is evidenced by the negative x direction velocities along the back of the square geometry and the curving of the streamlines seen in the streamline plot. For my circle geometry results, our Reynolds number was again set to 100, and convergence was ensured through the L2 error norm of velocities and spatial convergence. In comparison to the square geometry, we expect to see smoother streaming around the circle, which is achieved in our streamlines graph. We also see greater vorticity at the tail end of the circle, which is again evidenced by the negative velocity seen in the x direction and the curving vorticity seen in the streamlines. For angle of attack testing, I varied the angle of the inlet velocity from 0 to 45 degrees. Pictured here is the 10-degree angle of attack results. Vortices are seen forming behind the square geometry. These vortices lead into a wake that continues into the outlet boundary. As the angle of attack increases, the solution became more and more unstable, leading to divergence at 45 degrees. In conclusion, I was able to simulate square and circle geometries inside of a 2D channel flow, and I was able to add angle of attack artificially to the flow through inlet velocity manipulation. However, stability was not always possible, and this especially showed with the angle of attack additions past 45 degrees. Here are my references. Thank you and questions.